Tom Leinster is going to speak now, or Dr. Tom Leinster, should I say. He's a Chancellor's Fellow here, and he co-writes the N-Category Cafe blog, which despite its name has very little to do with N-categories. And even more prestigious an achievement than that, he's my supervisor. So yeah, thanks Tom.
Thanks Barry, and I'm a big fan of the YRM, so I was really happy to be invited here, and I'd like to thank the organisers for not only inviting me, but also organising. The attention to detail is amazing. So I think the named organisers and the ICMS staff have done an incredible job with this. In the first talk this morning, Ken Brown said that he wasn't going to insult your intelligence by telling you what a group is. I'm not going to do that either, quite, but I'm going to ask you to indulge me by, can you please raise your hand if you're sure you know what the definition of a group is? I mean, you know what a group is, you know the definition, you can write down the axioms if necessary. Just indulge me, please, and raise your hand. Thank you. Please keep your hands raised. So, I'm not going to embarrass you further. Please keep them raised. I'm not going to embarrass you further by asking anyone to tell me the definition of group. But imagine that I didn't ask one of you what a group is. I'm sure you'd say, you know, a group's a set equipped with a binary operation, blah, 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 blah. So, if you know what a group is, if you're sure you know what a group is, you must be even more sure that you know what a set is. Now, can you keep your hands up if you're sure you know what a set is? You're sure you could write down the definition? Right, so that's a small number, and I suspect that with age it will become smaller as the set theory course in your past recedes from your memory. And I want to first of all say that this is an extraordinary situation. Again, in Ken's talk first thing this morning, he was working over a ground field called K a lot. He didn't say what a field was, he probably knows. But imagine you chatted with him afterwards and you discovered actually he doesn't know what a field is. He just kind of assumed that he knew what you could do with them, and he didn't want to know the definition, but everything seems to work out all right, you know, good career and everything. I mean, you'd be shocked, and rightly so, but it's absolutely the same situation with everyone in sets. So, you might be imagining, if you haven't read my abstract, that I'm now going to chastise you and tell you that you really should learn the axioms for sets. And that's actually the opposite of what I want to do. Really, I want to concentrate on the kind of sociological observation that mathematicians use sets all the time, not just pure mathematicians, you know. Applied mathematicians talk about solutions, sets of solutions, differential equations. There's the word set in there, you hardly notice it. Everyone uses sets all the time. People very, very rarely make mistakes in what they do with sets, and most of them are just trivially fixed. And yet that's all without actually knowing the axioms for set theory. So there's some very strong sociological evidence that we don't need to know the axioms for set theory in order to kind of prosper and do accurate mathematics. So let me just sum up some of those things I've said. It's kind of some sort of anthropology. We use sets all the time. Every time, say, you take a quotient group or a product space or whatever, you're doing some operation with sets. We very rarely get things wrong, and very rarely even give it a thought. However, a very small number of mathematicians quote accurately any kind of axioms for set theory. So this is a very odd situation, and it suggests that actually we all carry around in our heads some body of subconscious principles for, you know, the operating principles that we use when we're manipulating sets, the thing that tells us that you can do this and you can't do that. So the challenge is to write them down. Now, that's a slightly misleading, a slightly glib way of phrasing it, write them down, because you know, everyone has slightly different intuitions, and one person's operating principles won't be quite the same as another person's, although somehow the net effect is always the same. And also they're going to be massively redundant if you do this. It won't be anything like an axiom system. But that's roughly the plan for this talk, is to talk about what the operating principles we actually use are and how they can be used to, as a system of axioms for set theory. And this isn't my solution. The solution is due to Bill Revere, and it's worth just having a look at the bibliographic details here. So this is very nearly 50 years old. It's in a very prestigious journal, and yet it's very little known. So I don't really want to speculate at length on film about why I think that is so. But I mean, there are reasons. If you actually want to read it, then the best thing to do is to download this. So green means it's a clickable link if you download these slides, and it's 35 pages rather than 5 pages. But anyway, this was Revere's radical solution to it. Now, I can say what the solution is in one sentence if you know plenty of category theoretic jargon. So the axioms say sets and functions form a well-pointed topos with natural numbers and choice. That's it. Now that's also the kind of description that's put people off, because most people don't know what those words mean, and therefore it makes it sound like it's something completely impenetrable. And I want to do something about that. Okay. Right, so the major point of this talk is that it is possible to solve the problem mentioned on the previous page, to write down a set of axioms for set theory that models quite accurately how we actually think about sets, and also that it can be done in a way that doesn't use any category theoretic language whatsoever, including the word category. And it's also possible to motivate without knowing any category theory. Now, of course, category theory is a great thing, but it's also worth appreciating that not everyone thinks it's a great thing. But the first thing I have to do before I get to any of that is answer the question, why bother with setting up another axiomatization set theory when there's already at least one that's very, very well known and well explored. So here we get to the second bit of anthropology. So what we're going to do is we're going to look at two things. On the one hand, how ZFC, Zermelo-Frankelwood choice, the dominant system, interprets the word set, and on the other hand, how most mathematicians interpret the word set. And I want to argue that these are very different. Actually, it's very unfortunate historically that the same word is used for both purposes. Before I do that, I need to kind of clarify things. So I've given some versions of this talk before, and there was one time when it went awfully, because it got a really heated emotional response, which is partly my fault for not being careful enough with my words. But there was one person who asked a question afterwards. He was so angry his voice was shaking. Another person asked a question afterwards who accused me of spreading propaganda. So I want to be very, very clear about what I think and what I don't think. I mean, there will be some things that some people disagree with, and that's okay. But I'm not making any criticism of the study of ZFC or other set theories that set theorists study for its own sake. I mean, there's very, very deep and difficult stuff involved there, and I think that people who are talented at studying it should study it. However, I do think that it does a bad job of modelling how mathematicians think about sets. This is a mathematical modelling tool, right? In the other lecture theatre, whichever way it is, Jonathan Sherrod is talking about modelling vegetation growth in arid landscapes. We're talking about modelling how mathematicians reason about sets. Right, so landscapes, mathematicians, but they're both, I mean, there's a very real modelling aspect to this talk. Okay, so before we even get to the axioms of ZFC, just kind of the preamble to the axioms. The first thing is that the elements of a set are always sets too. The only objects in play in ZFC are sets. This is definitely not so in ordinary usage. A typical set, such as the real numbers, the elements, you would never think of an individual real number, such as pi, as being a set. Right? And so what this means in ZFC is, given a set and an element of that set, you can ask what are its elements. You can always ask of a set in ZFC, what are the elements of the elements? And in ordinary usage, this simply makes no meaningful sense. If someone asks you this question, asks you what are the elements of pi, you just assume you misheard or something. So perhaps, I mean, that might be okay, because we might make a kind of gentleman's agreement to never ask such awkward questions or make such nonsensical statements. But that won't work either, because the actual axioms of ZFC, such as this one, are such statements which in ordinary mathematics are nonsense. So one of the axioms of ZFC, the axiom of foundation or regularity, says that every non-empty set has an element disjoint from it. So, you take capital X to be the real numbers. Which real numbers are disjoint from R? Is pi disjoint from R? Well, who knows? So it's just a meaningless question. And here's another axiom in ZFC, the axiom of union. What is the union of all the real numbers? And just, again, it makes no sense. So there's a very real disconnection between sets in the sense of ZFC and other membership-based set theories and sets as ordinarily used by mathematicians. Okay. Oh yeah, so one other thing I wanted to clarify is there are two things that are often mixed together in set theory books. First of all, there's the axiom system, typically ZFC, in an introduction to set theory. And then there's the idea that all mathematical objects can be encoded as sets somehow. And these points here are quite separate from the question of encoding. I mean, everyone understands that the encoding systems are somewhat arbitrary, and everyone understands that everyone understands this. No one is accusing anyone of thinking that these encodings are meaningful, but that's a completely different issue from this. Okay, so the very final bit of preamble is I want to nip in the bud 3 very common misconceptions about categorical set theory. So the first one is that there's some kind of war on, that it's category theory versus set theory. And as I mentioned, people tend to get very emotionally heated about this because there's some sort of subjective aspect to it. So this is not, what I'm about to describe to you is not a replacement for set theory. It is set theory. It is a set theory. It is a categorically flavored set theory. The second is that the axioms I'm going to tell you are somehow more sophisticated than ZFC, that you'd have to teach them at a later stage in the curriculum, if you like. And that's completely understandable when you see descriptions like the one I showed you about the well-pointed topos. But one of my missions is to show you that they're actually completely mundane and elementary statements. Just, in fact, I would say closer to intuition than ZFC, because there isn't this whole element of element thing going on. The final common misconception is there's some kind of circularity. So once you know it's categorical, you think, hang on. The definition of category involves a collection of objects and a collection of maps, and maybe collection means something like set. So the definition of category depends on the definition of set, and now once the definition of set depends on the definition of category. And so, but this isn't actually the case, because, well, the first thing is that the axioms can be stated, as I mentioned, without using the word category once. The second is that it's just, I mean, if you don't know what this means, it doesn't matter, but in the logic jargon, it's simply a first order theory like ZFC. So it's exactly as problematic or unproblematic as your classic set theories. There's no difficulty there at all. Right, so here's the plan for the rest of the talk. I'm going to describe this axiom system. I'm going to describe, first of all, the basic ingredients, and then the axioms themselves. I mean, I won't go through them in grinding detail. I'll give some sort of overview. And then I'll chat a bit about what the world looks like if you decide to forget about ZFC, classical set theories. Almost all mathematicians have forgotten about them. And adopt this as your axiom system instead. So how the world looks from this point of view. So that's the plan. Okay. So here are the primitive concepts. So again, take a kind of sociological point of view. You open the pages of some journal. You see what vocabulary mathematicians use concerning sets. Sets, elements, functions, subsets, equivalence relations, quotients by equivalence relations, blah, blah, blah. That's the kind of thing that's used. Now, I mean, typically, any axiomatization of anything seeks to be somewhat parsimonious, somewhat economical. So you choose some of the concepts as primitive and derive the others. And the classic choice, the ZFC choice, for instance, is to take sets and elements as the primitive notions and to derive subset, function, equivalence relation, and so on. The big difference in what we're doing and what Lorvier did is to take as primitive sets and functions, and in fact composition of functions as well. So there are 3 primitives, not 2, in case that worries you. And then of course I have to derive such things as element from these things. So that's a major shift already, and in fact it's enough to make some set theorists feel like, well, it's not really a set theory if it doesn't have membership as a primitive. But anyway, that's done. So we need to be able to derive the others, and in particular we need to be able to derive the notion of element from the notion of function. So before I do anything else, in fact, I want to show you how that works and spend some time on it, because it's actually I mean, it's kind of trivial, but it's also the most important aspect of all this. So here we are, elements as functions. So I'm going to start by what you might regard as cheating, which is to suppose that we know what it means for a set to have exactly one element without knowing what an element is. Now, I'll come back to that, and if you don't know it already, I'll show you how that's done, but it can be done. So just grant me that for the moment, that we can say what a one-element set is, knowing only what sets and functions are. And let's suppose that we have one, so 1. Then the very, very simple observation is that the elements of a set X are in canonical bijection with the functions from 1 to X. So you're simply picking out a point. So here's X. Here's your freestanding one-element set. A map from 1 simply picks out a point. That's it. So it's a complete triviality, but there's a danger that you'll think it's a trick. It's a kind of one-off. So I want to persuade you it's really not a one-off. It's actually a really common pattern in mathematics that you get this kind of thing happening. So here are some similar phenomena. So a sequence in a set is, by definition, if you like, a function from the natural numbers to that set. So these 3 kind of fried eggs here are meant to be x1, x2, and x3, or x0, x1, x2 here. A loop in a topological space is usually, by definition, a continuous map from the circle to x. So meant to think of n and s1 and 1 as somehow similar things. Here's a slightly more complicated one. A solution of this equation in a ring is a homomorphism from this special ring into your ring. So the idea, I mean, the first one, the natural numbers, what do the natural numbers look like? They're just a kind of freestanding sequence with nothing, isolated sequence with nothing around it. S1 is just an isolated loop with nothing around it. And this ring is just an isolated solution of this equation with nothing around it. It's the whole purpose in life of this ring is to contain a solution to this equation. So these are similar situations, and then a similar but much simpler one is the one I just drew on the board. That's an element of the set is just a map from the freestanding element, just an element sitting in isolation. And so that's the thought. So it's not some kind of sneaky little thing to derive elements as functions. It's actually it's part of a large stream of common thoughts. So it says at the bottom we'll define an element of a set X to be a function from 1 to X. So some people have a kind of yuck reaction to this, and that, you're willing to admit that there's a canonical one-to-one correspondence between elements of X and maps from 1 to X, but you don't want to say it literally is a map from 1 to X. And, well, there are a couple of things I would say to that. The first is, if you go back to sequences here, the first point, we don't actually usually think of a sequence as being the same thing as a function. We probably have one picture in our head of what a sequence is like and another picture of what a function is like, and they're not quite the same. And that's reflected in the fact that we use different notation for sequences and functions. You know, it's usually xn in brackets, not f or something. And that suggests that we think about it differently. Nevertheless, we understand and get along fine with the fact that it's most convenient to define a sequence to be a function of the natural numbers. The other thing to say is that, you know, if you really wanted, you could add elements as a further primitive concept to the axiomatization, along with sets and functions and their composition. But then you'd have to add in axioms guaranteeing that elements corresponded one-to-one with functions from one element sets to your set. And so you'd just be kind of making much less economical axiomatization. So in any case, this is the strategy, this is what we're going to go with. Right, so here we go with the axioms. And I promised you there'd be mundane statements about sets. Before I tell you the axioms themselves, I have to just say formally what we're axiomatizing. I said it informally, but here it is formally. Some things called sets, some things called functions with specified domains and codomains, and a thing called composition. Okay. If you've come up against ZFC before, I mean, I keep referring to ZFC, although it's sort of the thing I want to move to the side. It doesn't matter if you haven't met ZFC or other axiomatic set theories before, but anyway, if you have met it, then you'll know that it's of the form. There are some things called sets. There's a binary relation on sets called membership, and some axioms hold. Okay, so this has a similar shape. There are some things called sets, some things called functions, a binary operation called composition, and then some axioms hold. So the axioms. Right, informally, composition of functions is associative, and there are identity functions. There's a set with exactly one element. Now, you see already I'm using non-primitive terms, so I haven't said what one element means yet, but I will get to that. There's a set with no elements. A function is determined by its effect on elements. Two functions from x to y doing the same thing to all elements, they're the same. That's what equality of functions means. You can form Cartesian products of sets, sure. You can form function sets, the set of all functions from one given set to another, fine. You can form inverse images. I mean, you can form inverse images of any subset of y, but in particular you can take inverse images, pre-images of individual elements. Number 8 here is about characteristic functions, so a subset can be regarded as a mapping to 0, 1. The natural numbers form a set, and every surjection has a right inverse or section. And that's it. So these are all kind of bog standard operations with sets. In fact, a couple of years ago I took over the teaching of a second year course called what's it called? Foundations of Pure Mathematics. Is that what we call it? 2F? Yeah. Foundations of Pure Mathematics. And I discovered that I inherited some lecture notes from previous lecturers. So this is just a basic course, you know, includes some stuff about symmetries before the students learn what a group is. So it's really quite a low-level course. And it also includes some stuff about sets, very basic stuff. And the previous lecturers had included some version of every single one of these axioms. And I talked to them and they said, no, it wasn't at all deliberate to imitate these axioms. They just seemed like sensible things to put into an introductory few lectures on set theory. So these are all just standard things. Okay, as I said, I'm not going to go through all of them. It takes a bit of effort to make all of these precise, and that effort is not contrived. I mean, I can't take you through all of it. There's a risk you're going to think that the ones I choose to make precise, which are 2, 4, and 9, will be specially chosen to be easy. So what I'm going to do to try and dispel that suspicion is, I hope I've left enough time to ask you to choose one more axiom for me to do. Now, you could think that whoever I choose is a plant. So you could have some kind of voting system, but we're not going to go there. So I'm going to do 2, 4, and 9. So I'll just give you a minute to look at these axioms and decide which other one you want me to do. Okay, right, the axiom's going to disappear now. So the ones that I've chosen to do, the first one is number 2, because I want to explain this business of how you say there's a set with exactly one element without knowing what an element is. So the key definition, I mean, if you've done any category theory, you'll certainly know this. The key definition is a set is called terminal if for all sets x, there's exactly one function from x to your set. There exists one and any two are equal. You can be very pedantic about it. If you think about it, in your intuitive, naive picture of sets, a set should be terminal if and only if it has exactly one element. So that's going to be our notion of one element set. And the axiom is simply that there exists a terminal set. And it's rather easy to show that if you have 2 terminal sets, then there's a unique isomorphism between them. Well, isomorphism would usually be called bijection, but it of course means a function with an inverse function. So that makes it harmless to fix a one-element set. Now, you might feel the wool's being pulled slightly over your eyes when I just say, oh, it's harmless, it's harmless. It can be made completely rigorous and respectable. For that, I refer you to the paper whose archive number was on the opening slide. But it's kind of like saying the trivial group. I mean, if someone says to you, oh, blah, 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 the trivial group, blah, 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 and you say, which trivial group? Then you'll get a really strange look. Which is, I mean, that's, I'm not trying to intimidate you into saying that there's but it's not worth asking this question, but there is a way to make this perfectly respectable. But I'm not going to do it now. So anyway, it's harmless to fix one, and then you define an element of a set to be a map from one to it. So that's the definition of element. So we now, I mean, some of those axioms I showed you before use the word element. We now have the right to use it because I've defined what it means. Okay. So the next of the axioms I want to show you is axiom 4, which informally said a function is determined by its effect on elements. So here we need another definition before giving the axiom. So elements are a special case of functions. Evaluation is a special case of composition. I'll draw another picture to go with this, I think. So here's the one element set. Here's the map that is the element little x, or picks it out if you prefer. Here's a function f. What does this composite map do? It picks out the element f of x. So evaluating f of x is the same as composing f with x if you believe that the function is a map out of 1. Okay, so I mean, these two expressions are the same except for a bit of punctuation. They're just fx. You write them respectively, both are just simply f followed by x. So the axiom is now easy to state. It's just what I said out loud before. If you have two sets and two functions from the first to the second, and f and g do the same thing, two elements, then f equals g. That's just what the equality function is. I mean, it's, you know, it's a completely banal statement, but that's what these things are meant to be. So that's that. I thought I'd better choose one from near the end, again to allay your suspicion that I'm choosing the easy ones. So we're going to do natural numbers. The informal statement was the natural numbers form a set. So we need to, I mean, how do we access the idea of natural numbers? And what we're going to take is our crucial property of natural numbers is you can define things by recursion. Here's the picture. You have some set x, you have some map R from x to x. You start with a point A here. You can keep applying R to A and you'll get a sequence in x. So here's R of A, here's R of A, and so on. And so that's maybe called x0, that's x1, that's x2, etc. So that's all there is. So here's the statement. Whenever x is a set, A is an element of x and R is an element from x to x, there should be a unique sequence with the property that the first thing in the sequence is A, and you get the next one by applying R. And so the definition, the formal definition that goes into this axiom is a natural number system is a set n, which you're meant to think of as being the usual natural numbers, together with an element called 0 and a function s. S secretly stands for successor. You're meant to think of it as the map that sends n to n plus 1, with the property above, just with the notation slightly changed. So this equation here just says that xn plus 1 is r of xn. It's the same thing as this equation here. So that's the definition of a natural number system or natural numbers object, and the axiom is simply that one exists. Again, it's a little exercise to prove that if one exists, then there's only one up to isomorphism. And again, it's harmless if we just fix on once and for all and you know, draw it in a blackboard bulb. That's the axiom for natural numbers. Right. So those are the ones that I decided to do. How do we do this? Yeah, I think. 5.
8.
Right, now it's hard. Shall I do 5 or 8?
5. 8.
That was a clear 5.
You know what? I think I'm running out of time. I'm going to do 5, and then I'm feeling confident about time. I can do 8 too. Okay, so what's 5 products? Okay. I have to remember this now. Right. So if you're think about this, if you're a category theorist, then you'll know how to do this already. So I should address this to people who aren't category theorists. If you have you have sets I, x, and y. I'm kind of thinking actually of x and y as being spaces and I as being a time interval, but it doesn't matter, any sets. Then a map like this, you would often write some components like that. and you can recover F1 and F2 from F by projecting. So here's the first projection. So that's how you recover F1 from F, by composing with the first projection. And similarly, you recover F2 from F by composing with the second projection. So, so here's the definition. You take sets X and Y. A product of X and Y is a set P, which you should think of as being the Cartesian product X times Y, but I don't have the right to use that notation yet, together with two functions, which you should think of as being the projections. And I'll call these, what should I call them? Little p1 and little p2, such that whenever we have sets and functions oops. F1 and F2 from some other sets to X and Y. There's a unique map from I into the product, which we call F, such that satisfying. What I want to say that F of the first projection of F of t is F1 of t, and the second projection of F of t is F2 of t for all t and I. And the axiom is then every pair of sets has a product. Does anyone who asked for 5 want to express dissatisfaction with that? Or ask, sorry,
Is it unique isomorphism?
yeah, it is. Yeah. So most of these axioms that say something or other exists, you can then go ahead and prove that it's unique up to unique structure preserving isomorphism.
Then in order to really do something, you need to, whenever you have two sets, you really need to pick product. That's kind of annoying.
It's kind of annoying in DFC too.
Well, they actually, I mean, it's an annoying choice, but they actually have a good one, right? So if you take X and the set that contains X and Y as the definition of the pair, and then the set of all those, it's a bad choice. You never want to talk about it, but you have one in hand.
Well, yeah, I mean, there's some aesthetic choices involved here. You know, whether you want to say we choose on once and for all or not, and that's kind of independent of which. I mean, you can do that or not. I'm personally agnostic about it. Okay, so for number 8, number 8 is down at number 8. It does depend on some of the previous axioms. So what it depends on is the notion of inverse image. Okay. What I want to say. Right, so in ordinary life, you can talk about the characteristic function of a subset, right? So ordinarily, given a subset A of a set X, you can you get the characteristic function of A, which is a map from X to 0, 1, and it takes everything in A to 1 and everything outside A to 0. And one way of expressing the definition of the characteristic function, it's a unique map or function chi from from X to 0, 1, such that the inverse image of 1 is A. Okay? So we want our axiom to say something like, we want our axiom to say there's some subset. I mean, again, we're not going to be able to say the set 0, 1, these things don't make sense yet. We want to say there's some set with the property that for any x and any subset A of x, there's a unique chi with this property. Sorry, that wasn't too clear. I'll say it again in a second. There's a barrier here still because I haven't said what a subset is. Now, you actually don't really need to say what a subset is. There's too much sort of obsession here with what the names of elements are. It's enough if you say what an injection is. So of course I can write down the definition of injection, which I won't do because you all know what it looks like, but the axiom is as follows, or the definition is, so a subset classifier so it's a set which I'll call 2, because secretly it's meant to be this 2-element set, together with a special element which I'll call T, which secretly stands for true, and is the element 1 here, such that whenever X is a set and you have an injection from some other set into X, it has a characteristic function. In other words, there's a unique map chi A from X to 2 such that the inverse image of T is A. Now, I confess that there's something slightly wrong with this statement because you notice that the conclusion doesn't involve I. The reason why is that in axiom 7, the one about inverse images, a little bit of notation would need to be set up in order to make this make sense properly. But this, in essence, is what the definition is, and then the axiom is that there exists a subset classifier. Maybe I can get away without. Maybe I can make this a bit more respectable without introducing more notation. The inverse image of something always comes with an inclusion into the domain. So it's really saying that this inverse image together with its inclusion into X is the same thing as that.
That's chi A inverse.
Oh yeah, thanks. Yeah. Okay, any questions about that before I move on? Right, so we've now done 5 of the axioms. 3 needs no further elaboration, so we've actually done 6 of the axioms, and number 10 is pretty obvious too, so we've effectively done 7 of the axioms. We've done most of the axioms, okay, and it's all, and it takes a little while to get your head around descriptions like this and this if you haven't seen it before, but it's very, I mean, these are very, somehow, natural thoughts, even if they're not immediately obvious. They're kind of very ordinary parts of category theory, for instance. Right. So the very final part of this talk is, as I said, it's going to be just some kind of waffle about what happens if you decide to wholeheartedly adopt this as your system of axioms for sets. So whenever you write down any axiomatization of anything, there follows a period of lemma proving. So, you know, you write down the axiom for a group, you have to prove things like you have uniqueness of inverses, this kind of thing. And this is no exception. And actually, in a sense, the more clever, the more economical your axioms are, the more painful your period of lemma proving is. So the first thing to do is to define all the other basic set theoretic bits of vocabulary that every mathematician wants to have. So, yeah, subsets, you define equivalence relations, blah, blah, blah. And show how to perform the other basic constructions, such as taking a disjoint union of two sets or taking a quotient by an equivalence relation. And so you can do all this. Some of it's quite tricky. In particular, this one I've put up here, showing that you can take a disjoint union of any two sets, is really quite hard, but it can be done. And then basically, from there on, the development's pretty much the same as for any other set theory you're likely to have come across. So, for example, if you know what the natural numbers are, the usual painstaking construction of the integers is to say, well, an integer is a pair of natural numbers up to some equivalence relation, which is basically saying that they're the same distance apart. And it's exactly the same as here as if you were starting in ZOC. You'd say that Z is n times n quotiented out by some equivalence relation. So it kind of the two flows merge together after a little while. Now this talk would definitely be incomplete if I didn't say something about how strong the axioms are. And I'm going to do that in 2 phases. First of all, I'm going to say how strong they are in relative to mathematics as a whole. So Saunders Mac-Lane, one of the founders of category theory, when he was alive, used to say things like that these axioms suffice for almost all of mathematics. I think he wanted to encourage other people to make this precise, but he never made it precise himself. Another thing that you hear people saying is that no more assumptions about sets are needed anywhere in a typical undergraduate maths syllabus. There has been some more precise work. So very recently, for instance, quite recently, Colin McCarthy has shown that no more assumptions about sets are needed anywhere in EJ or SJ. So these are the magnum opuses, of the Grogan School of Algebraic Geometry. And I'm doing this because they're thousands of pages long. Now, it's clear that what he's done is not to go through every line of it and saying, oh, what does that use, what does that use, what does that use? But I think you can kind of basically flick through a whole chapter saying, oh, that's some commutative algebra. It's clear there are no demands on sets here. No special demands on sets. I think et al. Cohomology raises some interesting challenges, but what he's shown or claims to show is that actually rather less than these 10 axioms is needed for the whole of EJ and SJ. There are also some limitations that are known. So here's something that can't be done. It's the simplest known thing that can't be done. So here we have the natural numbers, the power set of the natural numbers, the power set of the power set of the natural numbers, and these are disjoint union symbols here. And we're taking that to infinity in a countable way. So these axioms can't prove that this set exists. unless of course the axioms are inconsistent, in which case they can prove anything. So, I mean, you can see that this is not a ridiculously arcane example, but it's also beyond, I suspect, what anyone in this room has ever used in their research, unless there are set theorists in this room. And in fact, as McCarthy's work shows, this is beyond what huge bodies of important modern mathematics do use. Okay, so that's some indication of how strong the axioms are relative to maths as a whole. But also we have some standards to compare the axioms against. So again, there's ZFC, which has been extremely well studied. So I'm going to state a couple of theorems on this page, and it seems that set theory always involves many sort of 3- and 4-letter abbreviations, and there are going to be some here. Lord Beer's axioms, the ones I've been talking about all along, are referred to as ETCS, the elementary theory of the category of sets. You can add another axiom, or actually axiom scheme. Axiom scheme is a family of axioms. It's usually a countably infinite family of axioms, as it is here. So one of the ZFC axiom schemes is the axiom scheme of replacement. The categorical version could also be called an axiom of first-order co-completeness. It basically says that whenever you've got any family of sets that's specified by some first-order formula, you can take its disjoint union. So, for example, big I here could be the natural numbers. Xi could be the I-fold power set of the natural numbers. Right, so that will give you the example on the previous page. So this R would guarantee that that thing on the previous page does exist. Okay, so some theorems were proved in the early 1970s. One of them is that ZFC has the same strength as these 11 axioms. In fact, the same theorems can be proved. They can be translated back and forth in a mutually inverse way. So, so if you're concerned about strength, then there you have it. ZFC is the same as the 10 axioms I showed you, plus this extra axiom scheme. You can also ask about ETCS itself. What's that equivalent to? Well, this also is extremely well understood, and it's been well understood for decades. It's a certain fragment of ZFC called BZC. I won't explain what this means, but it's a pretty large fragment. Again, as indicated by this work on EGA and SGA, you get an enormous amount just from ETCS or equivalently BZC. So this is all well understood and well explored. I'm kind of emphasizing this because there's a distraction that comes up sometimes when I've talked about this with set theorists, where they say, oh, but this is a tremendously weak system. And it's true that, I mean, I think set theorists think that this is a tremendously weak system because there's only a finite number of axioms. Whereas typically, I mean, ZFC, for instance, you have an infinite family of axioms. I mean, to I think most mathematicians, it seems like, if you can do all of EJ and SJ, it's basically, it's that close to being as strong as ZFC, but to set theorists, it's this close to being as strong as ZFC. But anyway, it's all a distraction because you can add or subtract this axiom scheme of replacement from either the categorical side or the traditional side, and you get some equivalences. Okay. The very last thing I want to talk about is about teaching. And one reason why is that when Lobbeer came up with his axioms, it was actually because he was teaching. And he had to, I didn't understand this story for a long time, because he said he had to teach calculus, and I didn't understand for years that in America, which is where he was working, calculus seems to mean all mathematics. So, I'm sure my interpretation, my understanding is a little bit crude, but that is often surprised by the things that are called calculus in beginning American syllabuses. Anyway, he was very dissatisfied with the set theory he was supposed to be teaching for the calculus, and so he just wrote these things down. So that's how it started. So there are some pros and cons to deciding that you're going to teach. I mean, if you're going to teach a course in axiomatic set theory, there are some pros and cons to using this rather than ZFC. So one of the pros is that the axioms are really relevant. And the first axiom says that sets and functions form a category. And categories, of course, are a very widely useful concept. About half the other axioms lumped together say that sets and functions form a topos. Toposes were introduced for reasons of algebraic geometry and nothing to do with set theory whatsoever. So all these axioms are meaningful, useful properties that it's useful in your mathematical life to understand, even if you don't care one bit about set theory. So it's useful for students to learn these things, even if they don't care about sets. Another thing is that there's a sort of notorious teaching or learning problem concerning learning about functions. I mean, an enormous, probably few of you, but many students find it extremely difficult to just use notation for functions correctly, understand what a function is, understand stuff about injections and surjections, and so I've sometimes found myself wishing that I could just spend some time concentrating on that and nothing else, and of course on this would certainly be an opportunity to do it. There are some drawbacks too. One of them is it's kind of new and exciting and therefore a bit of a challenge. There's, I believe, exactly one book on doing set theory in this way. And the other thing is that, and it's a bit of a kind of small drawback, that if you have a student who wants to be a career set theorist, well, it's just a fact that research level set theory is almost all membership based, far closer to ZFC than Lorbeer's axioms. I mean, I'm not saying that research level set theory has to be that way, but the reality is it currently is that way. Anyway, I better stop talking now. I hope I've convinced you that this is a set theory that does quite a good job of modelling what mathematicians actually do, and so we don't have to have one set of rules that we use all the time in our work and another one that we kind of put on a pedestal and maybe revere on a Sunday. You can actually use the same thing for both, and it's a good, practical, honest, workable solution. So thanks for your attention.
Any questions? More questions, so to speak?
Which book you mentioned as one book which uses?
It's by Lorbeer and Roseborough, and it's called Sets for Mathematics.
So a really bad sort of analogy would be to say take a language like English and say, okay, you've got a bunch of words here, pick any word, define that word. You have a sentence perhaps with more words, and you can sort of follow this down and down and down, and eventually you must sort of reach some circularity. I think if you try to define words purely with words, you would eventually have to take some leap, perhaps, some gentleman's agreement. Do you feel that maybe there's any analogy in set theory that eventually at some point you can't sort of notate with written language every single possible detail, that you have to make some step maybe perhaps, or...
I mean, I think that's really a matter of logic, not set theory. Set theory. I don't think it's particularly about sets. I think you could say the same thing about really any mathematics. You have to sort of understand. Yeah, you have to have some agreement about what that mark on the paper, how it's to be interpreted. So, yeah, I mean, I don't think I have anything new to add to that kind of old and distinguished question. Actually, yeah, that's a good point.
So, I mean, it was mentioned earlier that in ZFC you have kind of canonical, if inconvenient, constructions for it.
Well, that's not in ZFC, right? ZFC is a collection of axioms. That's some extra stuff that gets done in set theory books after ZFC axioms. But yeah, in the usual development, yes.
Yeah, well, yeah, it works in ZFC. So, and that in this, there are various sort of arbitrary seeming choices which seem to get in the way of that process. So obviously, if you can do all of maths in this, then you can perfectly well perform those constructions. I mean, you could presumably perfectly well construct the natural numbers as the empty set, the set containing the empty set, and so on.
If you wanted to, yeah, trees get involved. Yeah.
So how many, perhaps not a great question, but if one were to do that, would arbitrary choices creep in? And if so, how?
I mean, you could put them in if you want to. I mean, you can reverse engineer the whole of ZFC, but you can put them in if you want to, but you don't have to, I guess.
Yes. Thank you.
I saw a hand somewhere.
It's one of the.
So, you know, at the beginning you said a category, you have a set of objects and a set of morphisms, or something that's not necessarily a set.
Yeah.
In this set theory, what's this thing that you're calling set that's not a set?
I'm not calling it anything, I'm just, as I say, we're on exactly the same footing as with ZFC or any other classical thing. This is just something from first order logic. You simply say, we shall speak of some things called sets. I mean, of course, logicians, if you look at the logic text, they won't use the word things, it sounds too informal, but that's essentially the content of it. You don't say there is a class of sets, or there is a collection of sets. You just say, there are sets. There is membership, or there are sets and there are functions. I mean, it's a slippery point. But again, that's nothing special to this set theory here.
Yes.
This is probably very naive, and the two theories seem very much the same to me. But I mean, you said there was a gap between them. There's a difference. I mean, does this have any relation to things like the contradictions or what can be counted as sets?
So which two theories?
The traditional set theory
Yeah.
and the categorical set
Yeah.
theory. I mean, you said there was a gap. There's a difference between them.
Yeah.
Does this have any relation to what the actual theory, like what we consider to be sets, and the possible contradictions that would arise?
So if you're actually talking about logical contradictions, then no. That's when to say that two things have the same strength is to it tells you that one is consistent if only if the other one is. But it's true that it is a different conception of what sets are. I mean, I feel like the traditional conception is more like there is a universal set that's a set of all the apples and natural numbers and functions in a universe, and we can take any sub-collection of that. People talk about universal sets sometimes in introductory textbooks. Whereas this, there's no such idea that it's more like a set is just a bag of electrons. They're distinct but nameless. I don't know. That's a woolly answer, but that's the best answer.
Thank you.
How many axioms are the ZFC? The 10 plus 1 here on the left hand side.
Oh, I think it's a bit less. I mean, but I would say that I think I'm doing 7 or something. I'm not sure.
So it's not, so in terms of number of axioms, it's not
Well,
so.
some of them are axiom schemas, so it depends on how you count those.
Yeah, right. So one of them's really an infinite list, but
Aha.
even if you ignore the factors. But in order to get equivalency, we need an infinite list here as well. So yeah.
Okay. I don't know, does anyone else have any other questions? And if not, we can thank Tom and all have lunch, I guess.